Now, if you're still fairly new to programming, or you've just finished my accelerated Python course, you probably haven't covered object-oriented programming. I decided to leave that out of my beginner's course for two main reasons. First, you can code interesting projects with the lessons provided without needing to create your own objects and classes. And secondly, it takes a while to grapple and get used to the fundamentals of programming, such as knowing when to use loops, or how to implement functions effectively, and so on. Object-oriented programming introduces a whole new approach to constructing programs, and can take a while to get your head around, but it becomes extremely useful when dealing with very large code bases containing hundreds of thousands or millions of lines of code. Object-oriented programming offers more advanced capabilities and allows developers to more easily represent real-world concepts in software. First, we're going to start with the term object. An object can represent anything that has its own characteristics and behaviors. For example, a ballpoint pen has the characteristics of weight, the material it's made from, its ink level, and so on. And it has behaviors, such as being able to write, or make a noise when tapped on a desk. If we want to represent this in software, we can do so as a self-contained unit that has its own data and its own functions that operate on that data. These characteristics are also known as an object's attributes, and we can represent these as simple variables or more complex data structures like lists or dictionaries. And the functions that operate on this data or the object's behaviors are called methods. This process of bundling code into a single unit is known as encapsulation and is one of the four principles of object-oriented programming. By encapsulating data and code within a single object, it helps keep our code organized and modular and far easier to maintain when programs become large. A class is another definition you need to be familiar with. A class is our blueprint or template for the object we want to create. From this class, we can create as many independent objects as we want. For example, another object might be a specific enemy in a computer game. Each of these enemy objects share the same characteristics and behaviors. In other words, they all belong to the same class of object, but they all have their own unique attribute values. For example, they would have different positions on the map, and their ammo status would be unique to each enemy soldier, and so on. Okay, now we're finally going to get to some Python code and actually build these classes and objects. The most basic class definition looks like this. This will be the start of our enemy soldier blueprint, and we'll build upon it as we go along. And also notice, the first character of every word is capitalized. This is a common convention for class names and helps us more easily identify classes in our code. The parse keyword acts as a placeholder. We use it when we want to define a class, but don't want to add any attributes or methods to it yet. This simply means we can run our code and Python won't complain that the class definition is incomplete. The next step is to instantiate, or in other words, create a single enemy object. Instantiate is another one of those definitions you'll hear thrown around quite often. It simply means to create a separate area in memory for our single enemy object and copy over all the attribute and method definitions from our class blueprints. You'll probably also hear this being referred to as creating an instance of a class. This is pretty much saying the same thing. We're just creating a self-contained object that is built from the plans in our class definition. Now our class definition is currently empty, but we'll add some methods and attributes to it later. To create an enemy object, you can call the class as if it were a function, where enemy_1 is the object or instance, and we're letting the Python interpreter know we want our enemy soldier class to be the blueprint. Enemy_1 is now an instance of the enemy soldier class. If we now create a second enemy soldier, a second and unique area of memory will be set aside for that enemy soldier object, and it will contain a copy of the class blueprint as well. And to prove to you that they reside in different memory locations, we can print these objects to the shell. You should see the different memory locations on your computer, and on this occasion, because the addresses are very similar, they're most likely placed next to one another in memory. Currently, our enemy objects don't do anything because they don't have any attributes or methods. We can start adding attributes by directly assigning them to the objects themselves. However, assigning attributes directly is not considered best practice. We really want all our attribute definitions to be held in one place, in other words, in our class definition. And this is so we can better control and update our enemy soldier blueprint later on. So that being said, we're now going to define these attributes in our class definition, and we can do this with a special method called a constructor or an init method. The init method is used to initialize an object and is called automatically whenever a new object is created from a class. So when we run these lines and instantiate a new object, everything within this init method will be executed. And you'll notice in the shell, the print statement in the init method was printed twice because it was executed as soon as we instantiated a new object. And also notice that the init method starts and ends with a double underscore. This double underscore is also called a dunder and is used for all magic methods within class blueprints. The self parameter can be a bit confusing at first, but what we can do is print out its value to see what it contains. So we'll momentarily remove our second object and just focus on the first instantiated object. Now, we've already seen that enemy 1 has its own space in memory by printing it out, and here we're printing out the object again after we've instantiated it and viewing its memory address. Let's now go into our constructor method and print out the self variable. This print statement contains an F string explaining we're inside the init method and will display the contents of the self variable. When we run this code again, in a second, the interpreter will step through this code as follows. First, it will take note of our class definition. Then it will see that we want to create a new object from the enemy soldier class, and because our class has a constructor method, this indented code will be executed as soon as we create an object. Initializing will be the first printed to the screen, then the contents of the self variable, and finally our print statement outside of the class will be executed. You can see that the self and enemy 1 variables display exactly the same information, and that's the address of the object. This is because when our Python code creates an object in memory, this object is passed in automatically as an argument within the enemy soldier parentheses and is sent here as a parameter, which we've chosen to call self. Self therefore represents the current object being instantiated and only that object. Now we don't need to call this parameter self if we don't want to, but it is the convention when creating classes in Python. So now we can add the other attributes. Here, we've placed 5 extra parameters after the self variable. These instance attributes are prefixed with the variable self, letting Python know that these values being passed in belong to the single object that is being instantiated. Now, when instantiating an object, we need to place in the suitable argument values for the init method. And we can create a second enemy now with different instance attributes. And we can access the attributes of each object using dot notation. But what if we want an attribute to be shared among all instances of a class? In other words, we want all our enemy soldiers to simultaneously hold the same bit of data. In what situation would this be useful? Well, In relation to our enemy soldier, we may want all enemy objects to share the same running speed, because then we can easily control their difficulty level. So let's introduce this to our enemy soldier class. This here is called a class attribute. Now, class attributes are not prefixed with self like all instance attributes are. This is because a class attribute isn't tied to any one particular object. The class attribute belongs to all existing objects at the same time. We can demonstrate this here by printing out the speed attribute for both enemy objects. And the great advantage of this class variable is we can update the speed of all enemies in the game simultaneously by changing the speed value. If we had instantiated 5,000 enemies in our game, their speeds would have doubled by simply changing one line of code. Now, when the interpreter tries to access the speed attribute on our enemy object, it first checks the object's instance attributes to see if the speed attribute is present. If it can't find it here, the interpreter then checks the object's class attributes. We've currently modified our speed class attribute by referencing the class, but something counterintuitive happens when we replace the class with one of our objects. Here, we've modified the class speed, but on the next line, we've created a new instance attribute called speed for the enemy 1 object. So now, when we print out the speeds of enemy 1 and enemy 2, the interpreter will see that enemy 1 has an instance attribute named speed that is set to 50, and it will ignore the class attribute speed. But with enemy 2, the interpreter will not find a speed instance attribute because none was set, and will therefore jump up one level to the class attribute. It's generally not best practice to assign values to attributes directly like this. It's better to use setter methods, and we'll cover this properly later in the getters and setters section. So it's important to talk about instance methods now, because without these, we cannot perform any logic on our object's data. And it's really important not to confuse these with static methods or class methods. We'll cover those a bit later. Instance methods are associated with an instance of a class. This means they work only on the object. So in this example, we're creating a method that checks our object's current health, and if it's below 10%, we set our object's state to a retreating mode. The way we create methods is very similar to how we create regular functions, except instance methods must always take the instance or object as the first argument, just like we did with the constructor method. So here, we've created one enemy object with a health of 100% and in a state of pursuit, and we can see this here by printing out its state attribute. But now, we've set the health attribute for enemy 1 to 5%. When we call our check health method on our enemy 1 object, it's able to run a copy of this code here and set the object's state to retreat, and we can view this by printing it out here. We can write another method that can be called when our enemy soldier finds a health pack. Let's say this health pack boosts their health by a certain amount. We could write the method like this. Now we have two parameters, the self, because we're working on an individual object, and amount, which should be any positive integer. The if statement does something quite important here. It's saying that whatever health amount we receive, whether that's 10% or something ridiculous like 200%, our object's health will never be higher than 100%. So our enemy 1 soldier starts off with 25% health. We then run the health boost method on our object, passing in 50% health. Our new health should now be 75%. We're going to look at class methods now, and I'll show you how we can use them for our enemy soldier class. Class methods differ from instance methods in that they are bound to the class itself rather than the instance of the class. In this example, we use a class method to update our speed attribute. Now we've already done this by simply typing enemy soldier.speed equals 20. And by doing this, allowed us to update every object's speed within the game at the same time. But it's generally better to use a class method when modifying a class attribute because we can add additional control and validation checks before we change it. For example, it wouldn't make sense to update our speed with a negative number. Using a method also clearly demonstrates that modifying the speed wasn't just a mistake made by an overly tired coder. Calling the class by name shows that we understand how the class works and that we're clear in our intentions. This is our enemy soldier blueprint class that we made earlier. And we have our constructor method, which automatically runs when we instantiate an object. We also have our speed attribute, which belongs to our class as a whole. In order to create a class method, we need to type out a class decorator, and beneath that, we type the name of our class method. Now, because a class method always takes in the class as the first argument, it's convention to name this argument CLS. And to be clear, CLS represents our class blueprint, enemy soldier. We can now take in a second parameter that we can use to update our class attribute. And finally, we assign the speed value to our class attribute. This is very similar to how we assigned instance attributes in the constructor method using the self parameter. But this time, we're using the class parameter to let the interpreter know we intend to update the class attribute and not any individual object attributes. But as I said before, it's also useful to perform validation on the input. So here, we'll make sure the speed value is always positive. We'd probably want to add some more checks as well, but this is good enough for now. Okay, so we can test this out by printing out the initial speeds of our instantiated objects. Because the class attribute is currently set to 10, we should get the values of 10 for each enemy soldier. Then when we call our class method updateSpeed on the enemy soldier class, our class method should update our class attribute. You should see both objects have updated their speed values. And also notice that I didn't need to add the class name as a parameter. It was automatically inferred by the interpreter. We only needed to add the new speed value. Class methods can also be used for a different purpose. You may hear class methods being used as alternative constructors. An alternative constructor becomes very useful when we need to load in attributes of many objects from a text file. A use case may be when you're loading in saved game data from a file. After we've loaded this text file and placed each line into individual variables, we'll have something that looks like this. And here, I'm just focusing on the first 3 soldier attributes just to make it easier to understand. We would then pass each string using the split method, like so. And here, I'm separating each of our strings using a comma and a space as a delimiter, and each of these attributes gets saved into these separate variables here. I've also converted health, ammo, and the position data into int data types, so they are compatible with any methods that might want to perform calculations on this data. And now we can add these variables, as we've done before, via the constructor method to create each enemy object. But we don't really want to type out this code every single time we load an external text file. We can actually hide away all this code within our class and therefore keep it in one place using a class method as an alternative constructor. So here I'm creating a new class method using a class decorator and remembering to add the class as our first parameter. Again, it's just a naming convention to prefix our method with the word from. You're not strictly bound by this. It just indicates to other developers that this method creates new instances of a class without going through the usual constructor method. Now, our enemy string parameter will take in a line of text that we extracted from our text file. So for example, to instantiate a new enemy object, we would type out our class name and call our class method, making sure to send in our string of attributes. We can now copy and paste the parsing code into our class method. We also need to change this variable name here to match the enemy string parameter. And finally, we instantiate a new object by calling our class and inserting our passed attributes as arguments. This is exactly the same as when we instantiated a new object in the regular way. They both run the init method and create a brand new object. Using the return keyword here ensures that our new object is assigned to our variable named enemy1. It does take a couple of walkthroughs to get your head around, but this has simply allowed us to encapsulate all the logic of handling our text file data without us needing to worry about it. We can just plug in each string and it creates an object for us. And it's also worth emphasizing further that you could add in more validation checks and flexibility to this alternative constructor. Instance methods and class methods both pass in parameters automatically. Static methods do not pass in any parameter automatically. The purpose of a static method is to perform a specific action that relates to the class in some way, but does not depend on any attributes or methods of the class. Let's say we have a location on a map that has a particular size. With these map dimensions, we want to calculate the maximum number of enemy soldiers of this type we can spawn into this space without things becoming overcrowded. Let's write a static method for this. Now, we're writing this within our enemy soldier class because it relates to this soldier type, and it's a static method because it doesn't relate to any soldier object in particular. A static method typically has a static method decorator, and this just makes it clear to other developers what its purpose is, but you don't necessarily need to add it here. I'm going to name this method max capacity, and it's going to take in the length and width of the space. We'll also return the maximum number of units of this enemy type that is allowed to be spawned. The 20 here is just an arbitrary number that we've previously worked out to be the best value for this enemy type, and we're casting our sum into an int data type because we need a whole number when we return our soldier amount. To access this method, we simply call this method on the enemy soldier class and pass its return value into our max enemy soldiers variable. A space of 15 by 20 meters shouldn't have more than 15 soldiers. Inheritance is one of the 4 pillars of object-oriented programming, and it's a powerful feature that allows us to create a brand new class that is a slightly modified version of an existing class. We call this class a subclass or a child class, and the existing class a superclass or a parent class. Our subclass will extract all the attributes and methods from the superclass, but we can also write in new functionality in our subclass. And what makes inheritance so powerful is it gives us the ability to develop a logical hierarchy between various classes, and it also allows us to reuse code and avoid code duplication. So I'm going to clean up my enemy soldier class now, and we'll build it back up again as we progress through this section. Let's say we wanted to create a new enemy soldier that shares most of the same attributes and methods as our regular enemy soldier, but has its own unique features and abilities. Let's make this new soldier an elite soldier that is stronger and faster than our regular grunt soldier. Instead of copying and pasting the enemy soldier class and renaming it, we can link to it. We do this by adding the name of our superclass as an argument to our subclass. So here, we've created a new class called Elite Soldier, which is a subclass of the enemy soldier superclass. And with this subclass, we can instantiate new Elite Soldier objects. Because our Elite Soldier class does not have its own init method yet, it will inherit the init method from the enemy soldier class. And this constructor method is able to store these arguments as instance attributes for our Elite 1 object. We can test this out in the shell below. But because our Elite Soldier is meant to be superior to our regular soldier, let's increase its speed to 50. We can do this by creating a class attribute called speed in our Elite class. And this speed attribute will override the speed attribute in the superclass. So now, when we test our Elite 1 object, its speed will now be 50, but it will still inherit other attributes from the superclass or the parent class that haven't been overridden. If we instantiate a regular enemy soldier from our superclass, its speed should remain at 10. So you can see that all the objects that were instantiated from our enemy soldier class will not behave unpredictably if we decide to override attributes within any child classes. Now, our elite soldier can move a lot faster than our ordinary soldiers, but our elite soldier might need a couple of new instance attributes that the regular soldiers don't possess. For example, we could have an armor attribute, almost like the HEV power suits in Half-Life. But first, we want our elite soldiers to inherit health, ammo, position, and state from the parent class. And we can do this by defining an init method like before, adding in the self parameter and also our inherited parameters from the parent class. The only difference here is we're adding in our own armor parameter as well. In the next line, the super function is used to call the constructor method of the parent class, and this will pass in our elite soldier's health, ammo, position, and state up to our parent class to handle in its own constructor method. Because our armor attribute only applies to our elite soldiers, we can handle this here, like we do with a regular class. If we add an armor value argument to our Elite 1 object and run this program, we see our object now stores its armor value as well as health, ammo, and so on. But our enemy 1 object doesn't have an armor attribute, and if we try and call armor from a standard enemy object, we'll get an attribute error. Even though we've inherited all the attributes and methods from our parent class, we can introduce our own methods that only work with elite soldier objects. Let's say our elite soldier object has the ability to employ an invisibility cloak when their health and armor is higher than 50%. We can add a method to our elite soldier class to control this. Because this is an instance method, we include the self parameter. Our with statement checks our object's current health and armor status and only sets the cloaking attribute to true if we have enough energy. Now it's a good idea to set this cloaking attribute within the init method as well, because it ensures that it's initialized automatically when our elite soldier objects are created. As well as adding the cloaking attribute here, I've also included it as an optional parameter, which is preset to false as soon as the object is created. So when we create our objects like this, we can leave out the cloaking arguments without getting any runtime errors. When we access our cloaking attribute after instantiating our object, we see our cloaking is set to false. When we call our method on our object and test our cloaking attribute again, we see it's now set to true. But if we reduce our health and armor below 50, we should get the message printed to the shell. And finally, I'm going to talk about inheriting methods from the parent class and how to override these methods. So previously, we've talked about our static method called max capacity, and I'm going to reintroduce that now to our parent class. Now, just to be clear, any type of method can be inherited and overridden from the parent class. I'm just using this static method because it's a fairly simple example. But to recap, the purpose of the static method is to perform a specific action that relates to the class in some way, but that does not depend on any attributes or methods of that class. And they do not pass in any parameters automatically, like instance or class methods do. So our static method calculates the maximum number of enemy objects allowed in a room with a specific length and width. Because our subclass has inherited all the attributes and methods of our parent class, we can use this static method on our elite soldier objects. If I type in the shell elite 1 max capacity and put in a length and width of 10 meters, we should get a return value. And notice our elite soldier class does not need to own this method itself. But because this is an elite soldier, we might want to reduce the number allowed for the same area. We can override this static method by copying it into our elite soldier method and changing the code slightly. So by changing this value to 50, we should now return a value of 2 for a room of 10 by 10. Because our elite soldier class has a max capacity method now, the interpreter will now ignore the parent class's max capacity method. Effectively, we've overridden the parent class's method. So I've removed our subclass and stripped down our enemy class so I can explain getters and setters a bit more easily. Getters and setters are methods that we use to access or update the values of object attributes in a way that is more controlled and consistent than simply accessing the attributes directly. So previously, if we wanted to access enemy 1's ammo count, we'd simply print it out like this. And if we wanted to change its value, we'd readjust it directly like so. But ideally, we really want to access our object's attributes through a method. In order to retrieve our attribute values from our object, for example the object's ammo status, we would create a method named ammo and decorate it with the @property_decorator. This decorator is used to define this ammo method as a getter for a class attribute. Our getter will allow us to access the value of our ammo attributes in a controlled and consistent way. But before I finish the rest of this method, I'm going to prefix all the attributes of this class with an underscore. And this is just a convention, but it lets other developers know that these attributes should be treated as private variables, or in other words, they should not be called upon directly outside of the class. Now we can finish the rest of our getter method. And all we've done here is specify that we want to return the object's private ammo attribute when this ammo function gets called. Here, we're printing out enemy 1's ammo by calling the getter method. And notice that we do not include the parentheses at the end of the method name. One of the advantages of using a getter is you can add more functionality to this method. We might not want to return just the ammo count. We might want to return a high, medium, or low string value. Having an ammo value of 200 sounds high, but for this particular enemy type, it could be considered low. When we instantiate our object, we set the ammo to 20. When we call our getter method, we should now get a message saying ammo is low. And this might be useful if you want to print out this method above all enemy soldiers' heads in the game, it does kind of give the player an advantage. Let's write a setter method now for our ammo attributes. Setters also allow us to update a value of an attribute in a controlled and consistent way. Setters have a different type of decorator above the method name. They use the @nameSetter decorator, where name represents the name of the attribute you want to set. Our setter method must have at least one additional parameter after self. This value will be used to update our private ammo attribute. When we assign a new value to the ammo attribute, the setter method is called, and the new value is passed as an argument to the method. And you can also add in some validation checks here too, like making sure the amount argument is a positive number. And notice again, we exclude the parentheses when calling the method. And this is actually really important to take note of, because this exclusion of the parentheses is very useful, because if we have a large piece of code that previously accessed attributes directly, for example like this, you'll notice that now accessing the ammo attribute through our getter looks exactly the same. This will allow us to add getters and setters at a later date without breaking our code. We've finally reached the end of this object-oriented programming course for beginners, and I want to leave you with a challenge. Think about a simple project that fascinates you and try coding it using objects and classes. Some examples could include a simple game. It could be a physics simulation. You could make a password generator, and in fact I've done a video on this here. Or you could make an app that summarizes news articles in a couple of paragraphs. And I'm thinking of the ChatGPT API here. Whatever it is you decide to do, please share your creations in the comments below and tell us how you got on. Learning to code is hard and frustrating at times, but having an interesting project to work on and a community of supporters goes a long way to keeping us going. So make sure to practice, make sure to take care of yourselves, and hopefully I'll see you in the next video.